All right, so in this chapter, we are going to talk about some calculations, and some calculations we've already actually done in an experiment earlier, empirical formulas, molecular formulas. So let's get into it. The first thing we're going to talk about is atomic masses, and the atomic masses, again, are basically the fundamental properties of an atom, obviously made up of protons, electrons, and neutrons. But as you know, obviously, they're extremely small atoms, so you can't really just pop them on a balance or anything like that. So typically speaking, when we can't sort of directly measure something, we oftentimes will sort of assign something to use as a standard. And in the case of the atomic mass, which by the way is the number that we see there on the bottom of the periodic table, that's the atomic mass. And that is actually the carbon-12 isotope, which is what they use for the standard for atomic masses that we see up there. The carbon-12 isotope has 6 protons and 6 neutrons, and it has a mass of exactly 12 atomic mass units. And that, technically speaking, when you look at those numbers on the bottom on the periodic table, that technically is the atomic mass. And one of the sort of units that you can use for that is, if you pull it off, that is 1.008 AMU per atom. And that's sort of the units there. Again, atomic mass unit per atom. And we will very shortly, and as you probably are familiar with as well, we oftentimes don't use AMU as sort of a usable unit, since we use more grams as a usable unit. And we oftentimes will look at that number on the bottom as the molar mass, which we'll talk about a little bit later on here in this chapter. And we use it as grams per mole because, you know, we go to the balance, we don't get AMU, right? We get how many grams it is when we weigh it and stuff like that. But the atomic mass unit is exactly 1/12 that of the standard carbon-12 isotope. Now, when you look at the atomic mass, which is sometimes referred to as the atomic weight, what they essentially did for most part is just sort of compare the sizes, if you will, of other atoms to the carbon-12 isotope. And for example, hydrogen is about 8.4% as big as the carbon-12 isotope. And just do a little math there. That's basically 8.4% converted into a decimal. That gives us that 1.008 that we kind of see underneath hydrogen. Similar calculations have been done for obviously everybody on the periodic table. As we talked about earlier, again, that is not the mass number, but that really is the atomic mass, and also known as the molar mass as well. Now, when we look at these atomic masses on the periodic table, and especially since they chose sort of carbon as the standard isotope, when we do look at carbon, it does not actually say 12, but it does say 12.01. And that is because the values that we actually see on the periodic table are average atomic masses. They are the average atomic masses of all the naturally occurring isotopes for that particular element. And again, that's why we don't see, for example, 12 on the nose there for carbon. And you could actually calculate the atomic mass in AMU through this calculation. If you want to know the atomic mass in AMU, for example, you could take the percent abundance or relative abundance of the first isotope and times it by the atomic mass of the first isotope. You then would add it to the percent abundance of the second isotope times the atomic mass of the second isotope. And then you would obviously just continue that pattern for however many naturally occurring isotopes that you have. And it is, by the way, it is adding these together, not multiplying. People always want to kind of multiply when they do this sort of calculation, but it is adding in between each of those. What is the percent relative abundance? It's basically the percentage at which those isotopes occur naturally. So if you have all the naturally occurring isotopes, That should add up to 100%, right? Because then you have 100% of everybody. Obviously, if they don't add up the percentages to 100%, then you're probably missing an isotope somewhere, and you probably can sort of figure it out, just by subtracting from 100, what is the percentage it occurs at. So if we take something like carbon is actually about carbon-12 isotopes, about 99% of what you find, and the carbon-13 isotopes about 1% or so. And if we do this calculation using our sort of formula there, we could get the atomic mass. And again, it would be our percentage of our first isotope, which is the carbon-12. You can either move the decimal place 2 places to the left, or you can divide by 100, and it'll do that for you, whichever way you like. We'll times it by the mass of the carbon-12 isotope, which is 12 AMU. We will add it, again, converting this percentage into a decimal, divide by 100, or move the decimal point 2 places to the left. We'll times it by the atomic mass of the carbon-13 isotope, which is 13.00335 AMU. And when we add that all together, that is where we're going to get our value that we actually kind of see on the periodic table there, which is our 12.01, which we should relatively get there. And we'll end up with 12.01 AMU. So what we actually do see again on the periodic table is the average atomic masses, although most people don't call them average atomic masses, again, of all those naturally occurring isotopes. It's important to remember that although the sort of atomic mass of carbon is 12.01, in reality, if you could just pick out the carbon atoms, you would never find one that has a mass of 12.01. You would find one, for example, that is a carbon-12 isotope that has the mass of carbon-12, or you would find one that's a carbon-13 isotope that has the mass of 13 and some change. So again, we just sort of use these as our average sort of values. Again, that is how we sort of get those guys up there on the periodic table. The relationship between atomic mass unit and grams is that one atomic mass unit is 1.66 times 10 to the minus 24 grams. And what we will sort of see in a second or so is the molar mass, which is again a more common sort of unit, is numerically equal to the atomic mass in AMU per atom, as it is in grams per mole. But that is the relationship between grams and AMU as well. So again, if you were to go to the periodic table for carbon, one of the ways you could use those numbers is in 12.01 AMU per atom. And you really could use it as a conversion factor. You could flip it around and put the atom up on top, and 12.01 AMU. So if you want to know the mass of 431 atoms of carbon, we could use the atomic mass to do that. Again, just setting up a dimensional analysis. Opposites cancel, so the atoms cancel, and that leaves you with AMU, which is our 5176 there. Same thing with aluminum. If we look at aluminum, we see 2698. Again, you could pull that off the periodic table as 2698 AMU per atom. Or again, an atom has 26.98 AMU. So again, using our atoms in opposite locations so that they cancel, and this example here gives us 2024 AMU would be the mass of 75 atoms. Any questions on AMU there? I'll be honest with you, very rarely, probably outside of this chapter, will you do a calculation with AMU. Again, we typically use grams and molar mass and get our values in grams, which is, again, a more common sort of usable unit that we use. But technically speaking, that is technically what the atomic mass sort of unit is there. Definitely going to do that, so maybe. So how do you figure out, for example, the percentages of each of the different sort of isotopes that you have for an atom? You use something known as mass spec, and mass spec, basically atoms are molecules are ionized, they're kind of shoot down a tube, and they're basically broken up into fragments during this ionization process, and they are basically separated by a sort of an electrical field and also a magnetic field, and they end up being separated out by sort of size. So they come out on sort of the graph based on their size and their mass in different sort of areas of the mass spec. And there's also different sort of peaks, if you will. The largeness of the peaks will also kind of help you determine the percentages. So for example, here we see the chlorine 35 isotope coming out first, and we have our 37 isotope coming out. And again, just percentage wise, we can see a much bigger peak there at 35, which is about 75%. And, we're in that 25-ish, or a little bit more there for chlorine 37. So we could use this sort of technology to sort of identify what isotopes are present, their relative abundance based on the size of the peaks that come out. And here's sort of a mass spec. You send your sample through, heat it up, it gets ionized, it comes through an electrical field, and also gets bent there by a magnetic field. And again, they will come out on the detector, kind of lightest particles to heaviest. And again, you'll get some relative peaks happening there, like we just saw in the graph there, that will allow you to figure out those sort of relative percentages of each of those isotopes that occur. So if we have something like this, why don't you try it here? If copper is 69.17%, copper 63, with a mass of 62.9396 AMU, and the rest of it is copper 65 with a mass of 64.9278. What is the atomic mass of copper in AMU? So why don't you give it a calculation and see what you get here. Okay, so let's take a look. So we got a couple isotopes. So we got copper 63. It's about 69.17% of the time it occurs. It's got a mass of 62.99, no, 62.9396, 9396 AMU. We also have a second isotope, copper 65, and it has a mass of 64.9278 AMU. Obviously here we do need the percentage, so since they say that was the only two, we should assume that when these are together, 100% of it should be there. So we could just simply subtract from 100, 69.17%, and that will sort of give us our missing percentage there, 59.17, of about 30.83%. So this guy would be 30.83%. Now that we have both of our percentages there, we're good to go. So our atomic mass is going to equal, again, however you want to change the percentage into a decimal, you can move it 2 places to the left the decimal, times it by our molar mass, our atomic mass there. We are going to add it. You could also, if you choose, divide by 100 this thing, and it'll just move it for you, whatever you like to do. 64.9278 AMU. And if we do all that good stuff there, plus. Yeah, it looks like we get something like 63.55 AMU in this case. Should be pretty close to what we see there on the periodic table for copper. Any questions on that calculation there? So again, like this, sometimes you may be missing a percentage. So you again can kind of figure that out. You may be given the atomic mass or know the atomic mass from the periodic table, and maybe have to figure out the atomic mass of an isotope as well. So some variations on that. Any questions on that there? All right, just what we just did, I think. All right, so next thing we're going to talk about is really some more calculations here, a little bit more usable, if you will, that we use a little bit more often. And in chemistry, as you may know, we do have, or just in life, we have words that do represent a certain amount of something. So if we say we have a dozen of something, that represents 12. If we say we have a pair, that represents 2. If you say you got a gross of pencils, that's 144. So in chemistry, we also have a name that represents a certain amount of something, and that is the mole. And the mole is MOLE. The abbreviation for the mole is MOL. By the way, when you do see this abbreviation, that is the abbreviation for the mole. They had to get rid of something, got rid of an E. It is not molecules, which is very commonly mistaken by people. So usually in chemistry, if they want molecules, they will write out the word molecules. So if you do see MOL, again, that is definitely probably the abbreviation for moles and not molecules. Now, a mole of something is represents a certain amount, and that is Avogadro's number. And this is Avogadro's number with a bunch of decimals. And Avogadro's number basically is 1 mole of anything will basically equal 6.022 times 10 to the 23. The units here could be particles, they could be atoms, they could be molecules, they could be the classic pizza, right? Or shoes, whatever you like. Probably the occasional pizza question, but probably most of the time, though, the units here of Avogadro's number are going to be atoms or molecules, is typically what you will use it for. It really is, for all intents purposes, a conversion factor where you could, again, just set it up like a normal conversion factor. Or we got this going on here. Put the atoms up on top and the moles on the bottom. So you can use this conversion factor. It is the factor that allows us to go from basically moles to atoms, or backwards, atoms to moles, or again, molecules is also very commonly used. And again, that's Avogadro's number that's going to allow you to do that. Now, people sometimes learn Avogadro's number and they just want to use it in every calculation, and you definitely shouldn't do that. You should only use Avogadro's number if we have anything that is mentioning atoms, molecules, or something like that, or you're asked to solve for something in atoms, molecules. Again, if there's really no mention of those kind of keywords, atoms, molecules, you really should leave Avogadro's number on the side and not use it. So again, sometimes it gets overused where it shouldn't be used because people think they should try to use it. Now, probably a lot more common sort of calculation that we use is molar mass. And molar mass has units of grams per mole. We do find the molar mass off the periodic table. It is in the same location and the same number that we find the atomic mass listed on the periodic table. So we could say, for example, for hydrogen, this is 1.008 grams per mole would be the molar mass of hydrogen. We really could use it as a conversion factor. We could flip it around if we needed to and sort of do a dimensional analysis sort of calculation with it. The number always stays with the grams part, and it is always per 1 mole. Numerically speaking, the atomic mass and the molar mass are equal to each other. So if you do the conversion between AMU and atoms to grams per mole, they will equal each other. So they're numerically equal to each other along the way. We obviously can also use molar mass for molecules or compounds. So if you have something like water, to get the molar mass, we just basically add up all the parts from the periodic table. So we could go to periodic table and find oxygen, which is 16, and do 2 times 1.008 grams per mole for our 2 hydrogens, plus 1 times 16 for our 1 oxygen that is present. And that will give you 18.02 grams per mole as our molar mass for water, which again can be used as a conversion factor. Now, the molar mass is really your go-to calculation, probably for most calculations you're going to do. It is the calculation that goes from grams to moles, or backwards. Obviously, if you have moles and you want to get back to grams, it is the molar mass that allows you to do that. Now, the relationship between, say, Avogadro's number, molar mass, and everybody is this. Obviously, if you had 1 mole of hydrogen, that would have 6.022 times 10 to the 23 atoms of hydrogen. And if you had 1 mole of hydrogen, that would equal 1.008 grams of hydrogen. Right? So that is the way they are related to each other. If you had 1 mole of water, you would have 6.022 times 10 to the 23, and these would then become molecules of water, because water is a molecule rather than an element by itself, where we use atoms. And again, just tying those together, there would be 18.01 grams of water in every 1 mole of water. And for every 1 mole of water, there is 6.022 times 10 to the 23 molecules of water. So on sort of one end of the extreme, you have sort of grams. On the other end of the extreme, you have atoms or molecules. And the unit that ties them both together are moles, sort of in the middle. So obviously grams to moles, that is the molar mass. Moles to atoms or molecules is Avogadro's number. Atoms or molecules back to moles is Avogadro's number. And moles back to grams is the molar mass. So really both of these things are just conversion factors, where obviously the molar mass you get from the periodic table, and Avogadro's number is just a number that you have sort of available to you to use to go between those type of units. Any questions on that there? So let's try some here, I think, maybe. My eggs and marbles back. Here is a mole of all these different sort of elements. And again, there's our relationship between AMU and grams. And like I said, numerically speaking, atomic mass and AMU per atom is the same as it is per grams per mole. And again, using Avogadro's number in that conversion is what allows them to be the same. All right, there's our conversions back and forth. All right, so let's try one here. That was quick. Let's try a longer one there. Right. Calculate the number of grams of iron there is in 15.7 moles of iron. In case you can't see the periodic table, iron looks something like this, 5585. I take a few moments there and calculate it up. Okay, so we want to calculate the number of grams. We have moles. So the first thing we want to make sure, right, is we definitely don't need Avogadro's number here. There's no mention of atoms or molecules or anything like that. So this is really just obviously a moles to grams conversion. And that again is the molar mass from the periodic table that's going to allow us to do that. And that is 55.85 grams per mole. Or again, if we want to kind of use it as a conversion factor, we can put the moles up on top and the 5585 grams on the bottom. So just taking a dimensional analysis approach with calculation, 15.7 moles of iron. Again, remember opposites cancel, so moles are on top. I would clearly need moles on the bottom here. And we would do 5585 grams of iron per mole. Remember, when you set up dimensional analysis, you're always multiplying the top and dividing the bottom. So our moles here are going to cancel, and that should yield you 15.7 times the 5585. That's going to be like 876.845 grams of iron. Sig fig wise, probably looking at that guy with 3, so maybe an 877 grams of iron. Questions on that one there? All right, let's do lithium. So lithium here, 6.941. Once again, no mention of atoms or molecules. So in this case, it is a grams to mole conversion, still the molar mass we need. So right there means there's 6.941 grams per mole in lithium. Or again, you can use as a conversion factor flipped around. Once again, number always with the grams, and it's always per 1 mole. So setting us up here, 77.8 grams of lithium. Once again, grams up on top. So opposites cancel. We want to go that way with it. Moles of lithium and 6.941 grams. Again, multiplying the top and dividing the bottom is going to cancel out our grams. And we will end up with 77.8 divided by 6.941. 11.2 moles of lithium in this case. Also 3 sig figs based off of the original number there. Any questions on that one there? All right, continuing on here. So here we want to know how many atoms are there in 0.551 grams of potassium. Potassium a little 3910 perhaps. All right, let's take a look. So here we want to know atoms. So that should tell me Avogadro's number there is going to be involved. We are starting with grams. So we're basically got grams. We need to get to atoms. As we talked about a second ago, really the unit that ties those together are moles. So obviously this would be sort of our pathway. Grams and moles are tied together by the molar mass. And obviously moles and atoms are tied together by Avogadro's number. And again, that's going to kind of get us there. So we need the molar mass here of potassium, so we can just pull that off the periodic table. A little 3910 grams per mole. And again, we could use it as a opposite way as well as like my conversion factor. We're going to go here with 0.551 grams of potassium. Again, it's up on top, so making our decision pretty straightforward. Opposites cancel, so that has the grams on the bottom. Once again here, multiplying the top, dividing the bottom. And if we stopped right at this point, the grams would cancel. We would be left with moles at this point. Again, we could then use our Avogadro's number, which means 1 mole of potassium would have 6.022 times 10 to the 23 atoms of potassium. So we'll use that as a conversion. You could get an answer, or you could just continue on. And again, if you set up dimensional analysis, once again, it's going to make your decision making quite easy. Moles are on top. So again, to cancel, it's always opposite. So moles will go on the bottom. Avogadro's number there would go up on top. Little atoms there. Again, still multiplying and dividing. Moles are going to cancel, going to leave us with atoms, which is good. So 0.551 times 6.022 to the 23. We're then going to divide by what's on the bottom, 3910. And that's going to get us there 8.49 times 10 to the 21 atoms of potassium. That is a lot of atoms, but there's a lot of atoms in that many grams. Yeah? Any questions on that? Again, you can do each step individually, get an answer. Just try not to round, obviously, until the very end, like normal. Any questions on that one there? All right, let us continue on here. Let's actually do, maybe not that one. Maybe we'll do this one. Let's do how many moles are in 75 grams of C3H8O. So give that a go. And a couple information. If you need 12.01, if I put it, there we go. Hydrogen 1.008 and our oxygen there at 16. So give that a go. Okay, so again here, we're looking for moles. We have grams, nothing mentioned about molecules or atoms, so we do not need Avogadro's number. Again, we're just going to do our grams to mole, which is a super common conversion. We will need the molar mass of this guy here, so just going to add up the parts. So we got 3 carbons at 12.01 from the periodic table. We're going to add that to 8 hydrogens, 1.008 from the periodic table, and lastly, 1 oxygen at 16. That's going to give us a molar mass here of, looks like 6009. And again, in terms of molar mass, typically speaking, 4 significant figures is typically what you would take off the periodic table. It is also, by the way, what you typically would do your calculation of molar mass to in this particular case. Now, again, we're going to basically just use that as a conversion factor, and we can use it like it is, or we can also flip it around. So we'll take our 75 grams of C3H8O. Once again, just doing a dimensional analysis, opposites cancel. That means I actually do need to flip this around and put the grams on the bottom so that they cancel. And put our moles up on top. So we're left with them. And again, just going to multiply and divide, basically. Grams are going to cancel, and that's going to get us something here. And we'll go with, it looks like a 1.25 moles of C3H8O in this case. Yeah. Any questions on that one there? Now, also really important where people frankly screw up when they're doing molar mass is when they have something, say, in an equation, a balanced equation. So, for example, let's just say that this guy was in a balanced equation and it did have a 2 in front of it. Do I do anything with the 2 in terms of my molar mass? The answer is no. So when you calculate the molar mass, it doesn't matter if there's a coefficient in front of it in the equation. The molar mass units are grams per 1 mole. And what that 1 mole means is just the formula. So it's always just the formula. So if you're doing a calculation involving this guy in the equation, your molar mass would still be this, and you don't take the 2 into account, the coefficient. You take the 2 into account when you do stoichiometry, which we'll talk about in a later chapter, but not here. So molar mass is always just based on the formula, one formula, and what's in that, and that is how you calculate the molar mass. So you should never incorporate into the molar mass the coefficients in a balanced equation. Yeah. Any questions on that there? Now, another sort of wrinkle in this type of calculation is a question like this. So let's take a look at this question. This question wants to know how many hydrogen atoms are there in 72.5 grams of C3H8O. So in this particular case, we are actually not interested in the entire compound there. We're actually just interested in the hydrogen part. So we do actually need a way to go from like the whole thing to just the hydrogen by itself. And in this case, and in cases like this, you can actually use the formula as a conversion factor. And all the numbers that we see on the bottom, they actually represent the moles of each of those elements. And what that allows us to do by using the formula itself is we could actually come up with some relationships. We could say in 1 mole of that entire thing, we will get 3 moles of carbon, and that's where that comes from. We could also say in 1 mole of that entire thing, we are going to get ourselves 8 moles of just hydrogen. And we could also say in 1 mole of that entire thing, we will get ourselves basically 1 mole of oxygen. Again, if nothing's written there, then obviously it means 1. So we could actually have a bunch of kind of conversions that we could actually get from the formula itself, kind of a mole to mole sort of conversion. And because it is technically a mole to mole conversion, the first thing we would have to do in a problem like this is get our grams to moles. So we could use this as a conversion factor. So to get our grams to moles, we're going to use the molar mass. And I'm just going to borrow the one we just did, which should be this guy. So I think it was 6009 that we calculated on the previous problem there. And we would obviously get that from the periodic table, just like we did in the previous problem. So the first thing I'm going to do is take 72.5 grams of C3H8O. And again, just going to kind of do a normal dimensional analysis here to get rid of grams. So we're going to go 6009 grams of C3H8O, 1 mole of C3H8O. The grams are going to cancel. And if I stop right there, I'm in moles of the entire thing. Now that I have it actually in moles of the entire thing, now I could use that relationship that I got from the actual formula itself, which relates the entire thing to just hydrogen. And that's what's going to allow me to go from the whole thing to just hydrogen. And if I do that there, and again, you could get an answer at this point or just continue on. So I'm just going to continue on. I can go opposites to cancel. So moles of the entire thing will go on the bottom. And in this case, we have 8 moles of hydrogen. Again, basically, we are multiplying everybody on top and dividing everybody there on the bottom in this case. Yeah. Any questions on that so far? Yeah. You mean these? Yeah, no, you'd be fine. It's just I'm showing it so everybody understands a bit. Yeah. Probably I would think minimum you probably should write the relationship between the one you're using. Maybe it would be good. Yeah. Okay. So again, this is going to cancel out. We're now into moles of hydrogen. In this particular problem, we want atoms of hydrogen. So atoms is that key word that tells me Avogadro's numbers involved, right? And I can use Avogadro's number at this point, right, to get to my atoms. By the way, if I didn't want atoms, but I wanted grams, what could I use at this point? I could use the molar mass of just hydrogen, yeah, because we're at hydrogen at this point, right? So if we wanted grams at this point, we could also have used the molar mass if the question was different. So here we want atoms, so we'll just use our normal 1 mole of hydrogen is Avogadro's numbers worth of atoms. And we'll do that as our last sort of step here. 1 mole of hydrogen gives us 6.022 times 10 to the 23 atoms of hydrogen. The moles of hydrogen are going to cancel, still multiplying the top and dividing the bottom. So now popping that in there, 72.5 times 8 times 6.022 to the 23. And we're going to come back and divide by our 6009. Maybe hit the right button there. 9. There we go. And that's going to give us that we have in this case 5 point, we got there 3. 81 times 10 to the 24 atoms of hydrogen. So again, the ending on this could have been a little bit different. You could also go through and do it for any other element that's in there. You could do it for carbon. You could do it for hydrogen as well in this particular case. Any questions on that? So sometimes you will come across problems where they're not interested in the whole thing, just one element that's there. And again, the formula itself can be used as a conversion factor to go from the whole thing to each element. Any questions on that? All right, let's just do one more. Why don't we just do this one here? What is the mass? All right, let's take a look at this. So once again here, we want to know the mass of 1 molecule. So molecule obviously is Avogadro's number involved. And again, we're going to end up at grams. We're starting at molecules. Once again, it is moles that ties us to that. So Avogadro's number gets us the moles, and molar mass there gets us the rest of the way to grams. So might as well calculate that molar mass to begin with. Could I picked a longer one here? All right, so 8 times 12.01 for our 8 carbons. 10 times 1.008 from the periodic table for our 10 hydrogens, 4 nitrogens, 4 times 14.01 grams per mole, and lastly, a couple of oxygens to round it out there at 16 grams per mole each. That's going to get us, not that number. Let's see here, 8 times 12.01 plus 10 times 1.08 plus 4 times 14.01 and maybe a 32 there. 194.2, I hope, grams per mole. And we are then going to use that really as a conversion factor at the last part of our calculation. And to begin our calculation, we're going to obviously go this way here. So we're going to start with Avogadro's number. And obviously, in this case, 1 mole of caffeine there is 6.022 times 10 to the 23 molecules. So starting with what was given to us, which is 1 molecule. I'm just going to go with CAF. Be easier just to write caffeine. All right. We're going to then use, obviously, Avogadro's number here. So we want molecules on the opposite location. So we'll go Avogadro's number there on the bottom. Per mole of caffeine. The molecules of caffeine are going to cancel. At this point, we have moles. We are then going to use our molar mass, go the rest of the way. And again, we're going to use this as a conversion factor by setting it up in dimensional analysis. We can clearly see moles are up on top. So that tells us moles should go on the bottom and 194.2 grams up on top so that they cancel. Once again, multiplying the top and dividing the bottom. Basically nothing on top to multiply, so we're just going to divide 194.2 divided by 6.022 to the 23. And that's going to get us here 3.225 times 10 to the minus 22 grams of caffeine. Any questions on that one there? Question on grams, moles, Avogadro's number. Again, grams to moles, moles to grams. Lots of places using that calculation for sure. Yeah. Any questions? Okay, then we're going to talk about using these sort of calculations and also getting into sort of empirical and molecular formulas officially here. So one of the things that we can do with this is figure out, for example, the percent composition of an element by mass. And to do that, we basically would take the mass of the element we're looking at in the formula and divide it by the molar mass of the formula and our compound times it by 100. So if we have our C2H6O, we could calculate the molar mass of it here. And it looks like it is 4607. I'll write a little bigger here, 46.07 grams per mole. It's the molar mass of our C2H6O. Again, that is found from the periodic table. So if we want the percentage of carbon in that, since there are 2 moles of carbon, we would go 2 times the molar mass of carbon, 12.01 grams per mole. We would then divide it by the molar mass of the compound, which is 46.07 grams per mole, and times it by 100%. And that's going to get us here, divided by 46.07 times 100. I guess it's about 52.14%. So by mass, it's over 50% made up of carbon. We could do the same thing for our hydrogen. We'll take the percentage of hydrogen. And in this compound here, we got 6 hydrogens. So 6 times 1.008 grams per mole divided by the molar mass of the entire compound. And again, times it by 100% in this case. And that's going to get us 6 times 1.008 divided by 46.07 times it by 100. And get us about 13, it looks like, maybe, percent hydrogen. And lastly, our last element there is basically 1 oxygen. So the percentage of oxygen is basically 1 times 16 grams per mole divided by 46.07 grams per mole times 100%, right? And we'll take 16 divided by 4607 times it by 100, and it's about 34.73% oxygen. So by mass here, this compound is mostly carbon and oxygen, with about 13% being hydrogen. All the percentages should add up to about 100%. So as we talked about when we did that experiment, you could have at this point added this guy and this guy together and then subtracted by 100 to get the last percentage, right? And that's again, alternative way you could have got the last one along the way. Any questions on that? So percent composition by mass is used a lot, especially with empirical formula calculations and molecular formula sort of calculations as well. So let's take a look at those two things, which is empirical formulas and molecular formulas. So empirical formulas are the simplest whole number ratio of what is present, while the molecular formula tells you exactly what is present. So for example, again, if we had like C4H10, that is a ratio of carbon to hydrogen of 4 carbons for every 10 hydrogens in this case. We can reduce this down by 2 and still have whole numbers. And that would give us 2 carbons for every 5 hydrogens. And that would give us our empirical formula for this one, which would be C2H5, would be the empirical formula for the molecular formula over here. Same thing if you had N2O6, that is 2 nitrogens for every 6 oxygens. And you could also divide this by 2, which would give you basically 1 nitrogen for every 3 oxygens. So the empirical formula here would be NO3 for that molecular formula on this side. So if you can reduce down a formula to all whole numbers by dividing by a common number, those subscripts, that will give you your empirical formula. All, as we talked about maybe the other day or last time, all ionic compounds or ionic formulas are empirical formulas. And if you just think about again how we do an ionic compound, we put it together so that the charge equals 0 in the simplest way possible. So ionic compound formulas are always empirical formulas. Now, it is possible that the molecular formula and the empirical formula are the same. So H2O is basically 2 hydrogens for every 1 oxygen. You really can't get any smaller than that without not and still have whole numbers. So that is both the empirical formula and the molecular formula. So it is possible that the same thing could be for both if it's already sort of reduced down as far as it could go. Any questions on the differences there? So let's talk a little bit then on how we actually go about calculating empirical formulas. And really to calculate empirical formulas, there's a few steps that you want to follow. So if you wanted to calculate your empirical formula, the first thing you want to do is basically get everybody, all elements, into grams. And again, if you are given the percent composition like we just calculated by mass, you can assume usually that you have 100 grams of something. And that is because if you have, for example, like we did in the previous problem, it was like 54% carbon. If you assume you have 100 grams of that compound, that means you got 54 grams of carbon. Basically, the number stays the same. There was like 13 grams of hydrogen, I think, right? So you would have 13 grams of hydrogen. So sometimes, and very commonly in empirical formula problems, you're given the percent composition of each element. In that case, you could assume that you have 100 grams. And what that does is just keeps the numbers the same. You could assume whatever you want, but different numbers end up happening. So if you assume 100 grams, you keep the numbers the same. Once you have everybody into grams, you then want to go grams to moles for each element. And that obviously is a calculation we've been doing using the molar mass, right, to do that from the periodic table. At this point, you will now have moles of each element. And you want to divide by the smallest number of moles. So again, if you ended up with 2 moles of A after that second step and 4 moles of B, in this case, you would divide both of them by 2 moles. A double line there, 2 moles. And that would give you 1 here, and that would give you 2 here. And if you do that and you hit all whole numbers, that would be your empirical formula. So if you do that and you get all whole numbers are super close to whole numbers, like, just a little bit over, like 2.01 or maybe like, 1.98 or 1.97, then you are good to go. Again, if you say had a situation maybe like you had 2 moles of A and again 5 moles of B, and you go and divide by 2 moles on each of them here, you're going to end up with 1 there, and I believe 2.5 moles there. And in this case, this would give you an empirical form of AB 2.5. Problem is they need to be whole numbers. They cannot be decimals. So you do need to clear that. So you could do like a process like 2.5 times 1 is 2.5. 2.5 times 2 is 5. That looks like a whole number. So I do want to multiply everybody there by 2. So I would take this and multiply by 2. I guess multiply by 2 would go that way. And that would give me A2B5 as my proper empirical formula. So sometimes it's too far to round, and you need to find a factor to multiply that formula by so that you end up with all whole numbers. Common endings where it's considered kind of too far to round. 0.33, kind of too far to round. 0.5, a little too far to round. 0.25 as well, those type of things. So those are common sort of endings when you divide by the smallest number that is too far to round. Again, in textbook type problems, unlike in lab, in textbook problems, it needs to be like super, like almost right on the number or just above the number for you to do rounding. So typically speaking, those are common sort of endings where it's usually too far to round. Any questions on those steps? Let's finish up the last few examples here in this chapter. So we were just finished talking about how the steps to calculate empirical formulas, and again, in sort of textbook problems, we're not as sort of liberal in terms of the rounding as we are in the laboratory. Again, it does need to be relatively close to the whole number, either slightly above it or slightly below it. And again, like I said before, 0.33, 0.5 are very common sort of endings that are too far to round. So you definitely have to kind of fix it at that point. All right, so why don't we try one here? Determine the empirical formula for a compound that has a percent composition by mass of 24.75% potassium. 34.77% manganese, and 40.51% oxygen. Give you some numbers here: 3910 for potassium. Mn is what is that thing? 5494. 5494. And oxygen is 16. All right. So follow those steps we just talked about, also to your left there, and calculate the periodic table. Calculate the empirical formula. Be good. Look, see how you're doing. So again, we were given the percentages here by mass. Really, the first thing you definitely want to make sure of is just to kind of take a look at the percentages. And again, they all should add up to about 100% or in that ballpark. If they don't add up to 100%, then you're probably missing something, and there would be some way to figure that out. But in this case, it does add up to about 100%. And like we talked about earlier, we could just basically assume that we have 100 grams. And all that's going to really do is just keep the math super easy. We're just going to turn our percentages into grams. The numbers stay the same. So we would have 24.75 grams of potassium. We would have 34.77 grams of Mn, and we would have 40.51 grams of oxygen. At this point, what we're going to do is basically convert each of these into moles. So we would go to the periodic table there and get our molar masses. So again, we want grams on the bottom here. So 3910 grams per mole for potassium. We are going 5494 there for Mn. Again, grams on the bottom, so they cancel. And lastly, 16 for the oxygen, grams on the bottom, so it cancels. Again, in each of these cases, the grams will cancel each other out. Going to leave us moles of each of the elements. So 2475 divided by 3910, and we'll go 0.63299 moles of potassium. 34.77 divided by 5494, 0.6329 moles of Mn. And lastly here, 40.51 divided by 16, and 2.5319 moles of oxygen. At this point, once we've converted them all into moles, we want to divide again, always by the smallest. In this case, they're fairly close, but it looks like maybe Mn beats it out a little bit there. So we're going to divide everybody by the moles here of Mn. And we'll divide this guy by that moles as well. So that's essentially going to give us a 1, and perhaps a 4 would be good there. 0.6329 and a 4. We essentially hit all whole numbers. Basically 4.00 is 4. And since that's all whole numbers, that does give us the empirical formula, which would be KMnO4 in this case, a little potassium permanganate. Yeah, that's good. Any questions on those steps there? Yeah. So again, just convert it into grams, assume 100 grams to moles, divide by the smallest. All right, so this is one sort of straightforward sort of empirical formula calculation. Let's talk about another type of empirical formula calculation that's a little bit more experimental and a little bit more steps involved. And this is combustion analysis. And combustion analysis is typically when we take an organic compound, and if this organic compound typically will contain carbon, hydrogen, and oxygen, and we basically put it through a combustion reaction, which is reacting it with O2, and it will produce CO2 and water in this case. Now, what happens during this process is we are able to collect the CO2. We're able to collect the water that is being produced in this case. Now, from the mass of CO2 that you collect, you could actually figure out the mass of the carbon that you started with, because CO2 has carbon in it and nothing else has carbon in it. And since we do not lose any elements along the way, the organic compound is the only one that would supply the carbon that ended up in the CO2. We could also do a similar thing for the water that we collect. We can figure out the mass of the water we collected in this process. And from the mass of the water, we can figure out the mass of the hydrogen that we collected. Once again, the organic compound is the only one that has hydrogen in it. And all the hydrogen that ends up in water had to come from the organic compound. Conservation of mass, right? So we don't lose anything along the way. So it all has to kind of end up there. Now, one of the things that we cannot do, though, is we cannot figure out the amount of oxygen that came from the organic compound. And that is because the organic compound has oxygen. But what else do we put in there to do this reaction? We put oxygen in there to do the reaction. So some of the oxygen that ends up in the CO2 and some of the oxygen that ends up in the water is coming from the oxygen from this reaction and not the original organic compound. But that's okay because we know that our organic compound contains carbon, hydrogen, and oxygen. And from the previous couple of steps there, we could figure out the amount of carbon, we could figure out the amount of hydrogen. And if we know the mass of the organic compound we started with, we can then use that mass and the mass of the carbon and hydrogen that was collected to figure out the mass of the oxygen. So we could kind of subtract from the mass of our original compound, and whatever the difference is from the mass of carbon and hydrogen would be the mass of the oxygen that's present. So in combustion analysis, you have to do a few extra calculations at the beginning to basically get yourself to grams of carbon, grams of hydrogen, and finally grams of oxygen. At that point, it then just turns into a regular empirical formula type problem where you take those grams, convert them to moles, divide by the smallest number of moles, and you get your empirical formula. So there's a little bit more kind of prep work here in this type of analysis to kind of get to the grams of each of those elements before you can kind of do the empirical formula calculation. Any question on that there? So we're going to go through one here together just to show you how to kind of go through the calculation here. So we're going to take some ethanol. We're going to take 11.5 grams of ethanol, and we're basically going to run it through this process. We're going to heat it up. We have a water absorber, which is going to catch all the water that kind of goes through there. We have a CO2 absorber that's going to catch all the CO2 that basically goes through there. And in this experiment, we ended up collecting 22 grams of CO2, and we ended up collecting 13.5 grams of water. Once again, ethanol does contain those three elements, carbon, hydrogen, and oxygen. So like I said before, we're going to use the amount of CO2 that we collected to basically figure out how much carbon was there. So to do that, we're going to take our 22 grams of CO2. And remember, in this particular case, we are interested in not the CO2, but we're actually only interested in the carbon part of it. If you remember earlier today, we talked about that you could use the actual formula as a conversion factor to go from the whole thing to, in this case, just carbon. So we could use the CO2 formula and say for every 1 mole of CO2, we actually get 1 mole of carbon. And we could use that as a conversion factor like we did in that previous problem we did earlier today. We are also, for water, not interested in the whole thing of water. We're interested really in just the hydrogen part of water. And we could also use water's formula like we did earlier and say in 1 mole of water, there are 2 moles of hydrogen. So we're going to kind of use that whole thing to each element relationship that we did before, and that's going to allow us to get to grams of carbon and grams of hydrogen. Now, just like we did in that previous problem, before we could actually use those, we do need to get our CO2 and our water into moles. So in order to do that, we will need the molar mass of CO2. And CO2 is obviously 1 carbon from the periodic table and 2 oxygens, which are 16 from the periodic table each. And that's going to give us 4401 grams per mole as the molar mass of CO2. just thinking ahead, we will also need water's molar mass to do the similar type of calculation. So water here obviously is, I can get rid of some of that there, maybe. And water is obviously 2 hydrogens at 1.008 from the periodic table, and our 16 for our oxygen. And that's going to give us our 18.02 grams per mole. So again, I just know I'm going to have to use both of those, so I'm just going to calculate them up front. And now we will start our real calculation here. So we're going to use the molar mass of CO2, and we're going to convert it into moles of CO2. So grams need to go on the bottom so they cancel. At this point, if I stop my calculation, I'm in moles of CO2. Once again, we do want moles of carbon and eventually grams of carbon. So we'll use the formula as a conversion factor. And I'm going to do 1 mole of the whole thing, which is CO2, will give me 1 mole of carbon. And I'm actually going to get an answer at this point, and I'll explain later why I got the answer. It might be obvious. But that's going to give me 0.4, I'll call it 999 moles of carbon. But we also want to know how many grams that represents. So we will use the molar mass here from the periodic table of just carbon. And carbon's molar mass is 12.01 grams per mole. And again, that's what's going to get us to grams. And basically what this is going to tell us is 6.004 grams of that original 11.5 was made up of carbon, because all that carbon had to end up there. Any questions on that calculation so far? I'm going to do pretty much the identical calculation here for water, except obviously I'm going to end up with hydrogen at the end. So we'll take our mass of water we collected. We again are going to use the molar mass of water to convert that into moles, and that is 18.01 grams per mole of water. The grams will cancel. Once again, we're not interested in the entire water. We're interested in just the hydrogen. So we're going to use the formula like we did there to convert it from moles of the entire thing of water to moles of just hydrogen, which would be 2 in this case. And again, that 2 comes from the subscript from the actual formula. Again, I'm going to get an answer here. And 13.5 times 2 divided by 18.01. I'm going to go 1.4992, we'll call it, moles of hydrogen. I also want to know how many grams of hydrogen that represents. So 1.008 is the molar mass of hydrogen. So again, we want grams up on top, 1.008 grams per mole of hydrogen. And that's going to get me about 1.511 grams of hydrogen. So out of that 11.5 grams that we started with, about 6 grams of it was carbon, about 1.5 grams of it was hydrogen. And that is how we're going to figure out oxygen. Because remember, again, in this situation, we cannot use these numbers to figure out oxygen because, frankly, we added oxygen. So again, some of that oxygen that we added that's not part of the organic compound is going to end up there. So we could easily find out the mass of oxygen by just subtracting. We know we started out with a sample that was 11.5 grams. We have already calculated that 6 grams of it basically was carbon. And we also calculated that 1.511 grams of it was hydrogen. So if I subtract all those good things there, 11.5 minus 6.004 minus 1.511 gives me that the remaining 3.985 grams is basically the grams of oxygen. Any questions on that part? So again, we're kind of using what we collected to figure out carbon, hydrogen, We're subtracting to get the oxygen, and that again is because it contains carbon, hydrogen, and oxygen to begin with. Any questions on that? At this point, we essentially have everything we need for our empirical formula calculation. We have the grams of carbon, we have the grams of hydrogen, and now we have the grams of oxygen at this point. So we could actually now just kick it into the empirical formula calculation, right? So we're going to convert those grams into moles using the molar mass. And by the way, in case you were curious why I got a number, now I don't have to do it for carbon because I already did. Now I don't have to do it for hydrogen because I already did. So really the only one I need to convert back into moles is oxygen. By the way, if you're not sure, you're basically just doing that calculation this way. And I already have the answer, so let's go backwards and do it. So oxygen is 16 grams per mole. So we'll do that one. And now for oxygen, we will get divided by 16. 0.2491 moles of oxygen. So I'm just going to put all my moles out here. So we got 0.4999 moles of carbon. We got 1.4992 moles of hydrogen. And we just calculated our 0.2491 moles of oxygen. At this point, we're going to divide by the smallest, which looks like it is oxygen in this case. So we're going to divide everybody by oxygen. So we'll take this and divide by the moles of oxygen, everybody. 0.2491 and 0.2491. All right, so obviously that is going to give me a 1 for the oxygen. For the hydrogen, 1.4992 divided by 0.2491, going to give me basically a 6. And for the carbon, 0.4999 divided by 0.24, put the right numbers in, 91 is going to give me a 2. Pretty much hit all whole numbers. So now we have our empirical formula, C2, H6 and O, and there you go. Yeah, so this is combustion analysis, usually again used for some type of organic compound that contains those 3 elements, where you collect the hydrogen through the water, collect the carbon through the CO2, get the mass of each of those and subtract from the original to get the oxygen, and then just basically do an empirical formula calculation. Any questions on any of those there? So a little bit more complicated empirical formula problem, just a little bit more prep work to get to the grams. Then they just kind of give it to you in the problem. But basically the ending part is the same as a normal empirical formula. Any questions on empirical formulas here? All right, so with empirical formulas, there should be perhaps molecular formulas. There's the one we just did. Hopefully they agree. Let's see. There we go. They do. All right, so now we're going to talk about how you actually determine the molecular formulas. And there's really kind of 3 things that you need to determine a molecular formula. The first thing you need is you need the actual empirical formula. So that could either be just given to you in the problem, or you have to do like we've been doing, sort of calculate the empirical formula yourself. Once you have the empirical formula, you will also need the molar mass of the empirical formula. And the last thing that you will need is the approximate molar mass of the compound. The good news on that is in textbook problems, that's pretty much given to you. So somewhere in the problem, they'll say, hey, this compound has a molar mass of like 98 grams per mole. They may even give you like a range, like, hey, it has a molar mass that runs from like 90 to 98 or something like that, right? And that's because technically it's experimental when you determine your empirical formula and all those kind of things. If you're given a range, you could use either the high end of the range, the low end of the range, or you could use like the average in the middle of the range for the molar mass of the compound. They all will give you pretty much the same answer. You may be slightly different in terms of rounding, but you'll pretty much get the same sort of answer. So what do you do with all those things? You take the molar mass of the compound that's given to you. And again, if it's a range, low, high, or average, you divide it by the molar mass of the empirical formula, and that's going to give you a number. So let's just say you did that, and you got a number of 4 when you did that. Again, just making it up, obviously. And let's just say your empirical formula was C2, I don't know, H5, right? So what you would do is this number that you get here is what you would multiply your empirical formula by to get to the molecular formula. So my molecular formula in this case would be C8H20 would be my molecular formula. Now, sometimes people sort of write it like this, which I'm not a big fan of, but sometimes books will do this. They'll put like the little, put the right number there, put the 4 on the bottom. But I just think just multiply it out and get the actual formula would be a much better way. But sometimes people will do it that way. It's not technically wrong or anything like that. So we talked about rounding with empirical formulas, and typically we don't really want to round till it's really close. This place here, when we do this, we're a little bit more liberal in terms of how we could round it. So again, you could round to usually to the nearest whole number if it's not a whole number when you're doing this calculation here. The reason for that is the empirical formula and the molecular formula are related to each other by a whole number, basically. So again, especially if you have a range type of number, you may not get a nice, pretty, perfect number when you divide it. So you can usually round on this calculation to the nearest whole number. Most of the time, you'll still be fairly close to a whole number, but you can be a little bit more not so strict on the rounding on that one. Any questions on that there? All right, so why don't you give it a go here. A sample of a compound contains boron and hydrogen, 6.444 grams of boron and 1.803 grams of hydrogen. The molar mass of the compound is 30 grams per mole, basically. What is the molecular formula? So this is really 30 grams per mole. Boron is, what's that, 10 point something, 1081. Boron is 1081. Hydrogen 1.008. So again, a reminder, 3 things that you need to calculate molecular formula: the empirical formula, the molar mass of the empirical formula, and the molar mass of the compound. Good look. In this case, we aren't given the percentages. We're just given the grams, so no big deal. We could just roll with the grams. We are not given the empirical formula here, so we do need to calculate it. We are given, again, the molar mass of the compound, so we do have that, which is one of the 3 things that we need. So really, we're just going to kind of start with an empirical formula here. So we're going to take our grams and convert them into moles. So using the molar mass from the periodic table, 1081 grams per mole. We'll also take our hydrogen there, 1.803 grams of hydrogen, divided by 1.008 grams per mole. That's going to get us here 6.444, 10.81. Looks like 0.5961 moles of boron. 1.803 divided by 1.008, 1.789 moles of hydrogen. Here we're going to divide, looks like, by boron, which is the smallest moles. So that is obviously going to give me a 1 there. And maybe like a 3 there. Sounds good, like a 3. So we did hit whole numbers. So our empirical formula would be BH3. That would be our empirical formula. And that's the second thing that we need. And now we need the molar mass of our empirical formula. So the molar mass of our empirical formula in this case is 10.81 for our 1 boron, 3 times 1.008 for our 3 hydrogens. So 3 times 1.008 plus a 1081. And I'll call it 13.83 grams per mole. So what we do again is take the molar mass of the compound, approximate, and we'll take 30 grams per mole, divided by the molar mass of our empirical formula, 13.83 grams per mole. And in this case, again, may not be a nice pretty number. It's like a 2.17, and that's pretty close to a 2. Again, you can be a little bit more flexible on the rounding here. And that means that our molecular formula would be B2H6. We're basically going to take that 2 and multiply everybody in there by it. Any questions on that one there? Okay, so let's try one more here. A phosphorus oxide contains 43.64% phosphorus, 56.36% oxygen. Experimentally determined molar mass 283. Both the empirical and molecular formula, so we need the empirical formula to get to the molecular formula. In this case, we are given the percentages. Let me just take a quick look at it, and it is pretty close there to 100%. So we're not missing anything. In that case, we can assume 100 grams. And again, the purpose of that just keeps all the numbers the same. So that means we would then have 43.64 grams of phosphorus. We would also have 56.36 grams of oxygen. Next step on our empirical formula path is to convert those grams into moles using the molar mass from the periodic table. So we got 3097 for our phosphorus, and we got 16 there for our oxygen. That's going to give us for our phosphorus 43.64 divided by 3097. We'll call it 1.409 moles of phosphorus. For our oxygen, 5636 divided by 16, 3.5225 moles of oxygen. Here we're going to divide by the smallest, which looks like it is phosphorus, so 1.409 moles divided to both here. It's going to give me 1. And in this particular case, we will end up with 2.5. So that's going to give me an empirical formula, PO2.5. Problem with that is we need whole numbers. So this cannot be our empirical formula. And again, that is too far to round. So like I said before, kind of like 0.5, 0.33, a little bit too far to round. So we just need a factor to get ourselves to a whole number. So if we take 2.5 times 1, that's 2.5. 2.5 times 2, that is 5. So the 2 is the factor we want to use here. We want to multiply this entire thing by 2, and that will give us P2O5 as our empirical formula in this case. Any questions on that there? Now that we do have the empirical formula, that's one of the things we need. We also need the molar mass of it, so let's just get that. So 2 times phosphorus, 3097. For our molar mass for our empirical formula, 5 times 16. And that'll give us the second thing that we need. So 2 times 3097 plus 5 times 16. 141.9 grams per mole. The third thing that we need is the molar mass of the compound, which is always usually in these type of problems given to you. And that was given to you. And that's the molar mass of the compound. So now we have everything we need to get to our molecular formula. We're going to take the molar mass of the compound that was given to you, 283.89. We're going to divide it by the molar mass of our empirical formula, 141.9. And that should give us a factor by which to multiply our empirical formula by. And in this case here, that is going to give us a factor of 2. So we're going to then multiply our empirical formula by 2. Gives us P4010 as our molecular formula. First off, any questions on that calculation? Now, there is an alternative way that you could do this problem, especially since you are given the percent composition by mass. So an alternative move would be, flip the page, maybe 4364. I'll do it over here. 43.64% phosphorus. We got there 56.36% oxygen, and we were given the molar mass of 283.89. 283.89 grams per mole. So because these are the percent compositions of each of these elements, we could actually just start with the percent composition and turn it into a decimal. You divide it by 100 or move the decimal and take 0.4364, which is this guy, obviously, divided by 100%, turn it into a decimal. We could take that percentage basically and times it by 283.89 grams. And what that's going to give you basically is how many grams of that 283 is phosphorus. So if I do that, 0.4364 times 283.89 gives me 123.89 grams of that compound was made up of phosphorus. I could then take the molar mass of phosphorus, which was 3097 grams per mole, and divide that by 30.97, and I end up with a 4. I could then do the same thing for my oxygen, turn that into a decimal, times it by the molar mass of the compound that was given to you. And that will tell me how much of that compound is basically grams of oxygen. 0.5636 times 283.89 gives me 160 grams of oxygen, which then I could divide by the molar mass of oxygen. And that's going to get me a 10. And these numbers would represent the molecular formula. So you could actually start with the molecular formula here. And once I have the molecular formula, I know the empirical formula is the simplest ratio of that, which means in this case, to still get whole numbers, I could divide everybody by 2 and reduce that down to P2O5. And now I have the empirical formula. So if you do have the percent composition by mass, you could, and you know the molar mass of the compound, or the approximate molar mass of the compound, you could actually hit the molecular formula first and just reduce it down to the empirical formula, which is another approach. If you don't really have the percent composition by mass, no sense calculating to do this method, you could do the other method. Or you could still do the other method. As you can see, they both give you basically the same answer. Any questions on that method there? Questions on how to calculate empirical formulas, molecular formulas, grams, moles, Avogadro's number, percent composition by mass.